Alrighty, as most of you guys are probably aware, Jaren had a debate with Witsit yesterday, but unfortunately it was behind a paywall and won't be released on YouTube for probably a couple of weeks. But I begrudgingly forked out the $65 to Witsit to get early access, and you guys are the lucky benefactors. I do have to say that Jaren did exceptionally well in the debate. It's a little bit sad for me though, because there wasn't much opportunity for a really deep dive into any particular topic. But one topic that did come up a lot was the fact that on the surface of the Earth, it's an empirically measured fact that if you move 69 miles towards a star, then the star rises by 1 degree, and if you back away 69 miles, it drops by 1 degree. And Jaren did a pretty good job pinning Witsit on this. But like I said, there wasn't much chance to go very deep in that debate setting. So that's what I'm going to do now. So let's look at the first clip of Witsit Derp, shall we?
We're going to claim that all the stars in the sky are infinite distances away. So far away that when we move across the surface of the Earth and it looks like they drop down when we move further away from them, it isn't because of perspective. How perspective changes everything else in the world. And when we see a plane fly away from us and it goes down, right, and it comes close to us and it goes up, perspective affects everything in the world. We use special pleading, which is claiming the exclusion to a universal principle, the exception to a universal principle, which is no, actually the sky is the one exception, the star is the one exception. Perspective doesn't change it. It does exactly what perspective would do to change the position, but it isn't because of perspective. And then to make that, so we have to presuppose that to even claim the globe is possible. That's why they've changed the distance so many times and kept pushing it back. Then to claim that those stars are that far away, you then have to answer the question of how would you be able to see it from that far away? So now you have to assume that there is a vacuum, that there's nothing between us, a near perfect vacuum, so you could even see them.
1 minute.
And then you stack those on top of each other to come over and say, therefore, we're physically changing direction. It makes the perspective look as if it would if we were on a horizontal plane, but it's not perspective.
All right, so let's go over the main points of what he said. Witsit is correct that perspective is not the reason for stars rising when you move towards them and lowering when you move away from them. And his explanation is also correct. The stars are very far away, and I'll give you a very simple demonstration of that in a minute. But then somehow he claims that this is a special pleading fallacy, which is weird. Like immediately after he sort of perfectly explains that the globe model entails distant stars. So the distance you move over the Earth is completely insignificant compared to the distance to the stars. So for all practical purposes, you're not actually getting any closer or further away from the star. And therefore the angle isn't going to change for that reason. But he just likes to throw around fallacies. It's like he has this fallacy Tourette's. All right, so I'm going to jump to the fourth line here for a second, that we have to assume that there's a vacuum. That's not an assumption, that's a measurement. There are stacks of amateur balloon, stacks of amateur rocket launchers that measure the pressure on the way up. My favorite one is from a flat earther, Dwayne Kellum, and he measured a 99.5% drop in pressure between sea level and 120,000 feet. Right, so the key things that Austin said that are complete dog shit are the third and the fifth ones, where he says, it does exactly what perspective would do to change the position. And the bottom one, it makes the perspective look as if it would if we were on a horizontal plane. I have no idea how he said that first one with a straight face. All right, so let's have a look at how perspective would affect the stars if we were on a flat plane. Okay, so here is a really simple GeoGebra that models what perspective looks like on a flat plane with relatively close stars. But this model could equally apply to something like a tree or a building, or the usual example that Flurfs bring up, which is a row of streetlights. So as you get closer to it, it gets higher, and as you get further away, it gets lower, and eventually converges at your eye level. So we'll start off with the usual example that MC Toon gives. He's in Minnesota, which is roughly 45 degrees north. And if there is 69 miles per degree of latitude, then he must be 3,105 miles from the North Pole. And since our latitude must match the elevation angle to the pole star, then if you do the very basic trig on that triangle, just like you would do the trig if it were a tree or a building, then the height of the star must be 3,105 miles. Now, the problem is that if we move to 35 degrees north, we would have to travel 690 miles south. And since our latitude must match the elevation angle to the pole star, then it should also be 35 degrees. But that's not what the angle would be on a flat Earth. If you redo the trig with that new distance, you get an angle of 39 degrees, way off. The same happens if you move to, say, 55 degrees north. You'd travel 690 miles, and the latitude should match the elevation angle. But if we have, two sides of a right angle triangle, then that angle will be 52 degrees, not 55. So on a flat plane, the relationship between the distance to the North Pole and the elevation angle to the star is not linear. It's not 69 miles per degree. And it does not matter what height the star is. I'll leave a link to the Geogebra in the description if you want to have a play with it. Okay, so let's look at why in reality we measure 69 miles per degree of latitude. So here's our sphere Earth with a radius of 3959 miles. And once again, we'll start off with MC Turn's 45 degree north latitude. So the pole star is directly above the North Pole, but I've set the distance so far away that this line of sight to it is virtually parallel to the y-axis. All right, but if I bring the star closer, you'll start to see that the line of sight to it is no longer parallel. All right, so that black line is the observer's horizontal baseline, which is just perpendicular to down. And then I've asked Geogebra to measure the elevation angle between that horizontal line and the star. And obviously at 45 degrees latitude, that elevation angle is 45 degrees. The red line is the measured arc length between the observer and the North Pole. And since this is a circle, then that's going to correlate directly to the number of degrees of latitude. So the circumference of the circle is 3959 times 2 pi, which is 24,875 miles. Divide that by 360 and you get about 69.1 miles per degree. So no matter where you move this slider, that relationship between latitude and distance is linear. But not only does the Earth need to be a sphere, but the stars also need to be very, very far away for this relationship to hold. All right, so you'll notice as I bring the star closer, this relationship of 69 miles per degree starts to break down. So here we have 53 miles per degree, and that changes a lot with latitude. That's if the stars are close. All right, so again, this linear relationship that is measured in reality can only be satisfied by the Earth being a sphere and the stars being very far away. All right, so how do we know that the stars are very far away? Well, there are lots of clever ways we know the distance to stars, but this one is probably the easiest one to understand. So imagine that this black square is part of the night sky right above your head, and there are 4 equally spaced stars in a square. Now, you could do this on a computer screen, or you could literally print this out and stick it on the ceiling. It doesn't matter. But let's say you stick it on the ceiling. You look straight up, and the stars still form a square. Now, walk a few steps to the right and look at the stars again. What do you see? You see a rectangle, right? And you see a rectangle because you moved a significant distance relative to the height of the ceiling. Now, imagine instead of moving a few meters, you moved like a tiny fraction of a millimeter. So obviously if that happens, you're still going to see a square. And this is the same for observers on Earth. So even though observers might be separated by thousands of miles, that is utterly insignificant compared to the distance to the stars. So everybody on Earth sees the same constellations in the same formation. And while we're on the topic of parallax, there's a little Easter egg in celestial navigation called horizontal parallax, which is this HP column on the right. So this is an excerpt from the Nautical Almanac for January 1st, 2025. And you'll see the HP value for the moon is 57.4 arc minutes. This is probably a topic for another video, but you can actually reverse engineer the distance to the moon from this value. All right, so 3959 divided by the tangent of that angle gives you 237,000 miles. Wow, I wonder why we get that number. The Almanac also gives you horizontal parallax figures for Venus and Mars, because guess what? They're usually the two next closest celestial objects from Earth. They don't give these values for, say, Jupiter and Saturn because, they're so far away, they don't have any meaningful parallax for two observers from Earth. Anyway, getting back to 69 miles per degree, have to come clean now. I have been lying to you, lying right to your face. It's not perfectly 69 miles per degree. And the reason for that is because Earth is not a perfect sphere. It's oblate. And why is it oblate? Because it's rotating. And pretty much just for shits and giggles, here's a photo of Jupiter that I took earlier this year. You can also see a couple of the moons if your screen is decent enough. But what I really want you to look at is Jupiter itself. So first of all, the red spot looks like it's in the top hemisphere for me in Sydney. But for you guys in the northern hemisphere, it might be upside down. I wonder why that is. It's possibly because we are oriented differently. Maybe I'm upside down relative to you. But anyway, look at the shape. So here I've overlaid a perfect circle over the top. And you can quite easily see that the poles are a little bit squished while the equator is a little bit chubby. And now this is quite noticeable on something like Jupiter because it's massive and it rotates every 10 hours. You can actually watch the red spot move over the course of a couple of hours of watching. Anyway, since the Earth also rotates, the Earth is also oblate. So let's have a look at that and how it relates to the 69 miles per degree rule. Okay, so I've started off here with a perfect sphere, so a flattening of 0. And you can see that the radius on both the x and the y axes is about 3959. Now what I'm going to do is hit this button that says Earth Actual Flattening, which will turn this perfect circle into an ellipse that matches the dimensions of Earth. All right, ready? Keep your eye on one of the axes here. Ready? Go. Boom. See, it moved fuck all, like barely a pixel. So the polar radius of Earth is 3950 miles and the equatorial radius is 3963 miles. And that's not much difference. So when flirts show you a picture of Earth from space, and claim we're looking at a perfect sphere, you've actually got to get down and measure the pixels. Anyway, what I want to demonstrate with this GeoGebra is that the number of miles per degree of latitude varies very slightly depending on your latitude. So remember, latitude is defined as your angle to the celestial pole. So this guy at 10 degrees north latitude, is making a 10-degree angle between his local horizontal and the celestial pole, which again is effectively an infinite distance away. But look what happens to the distance between the observer and the equator when I make the Earth really squashed. Are you ready? Right, that distance gets a lot shorter. So instead of being 690 miles for that 10 degrees of latitude, it's going to be less. All right, now let's move the dude up to about 80 degrees latitude. 80, there we go. And see what happens to the distance between the observer and the North Pole when we squish the Earth. That distance gets further. So instead of 690 miles, it's going to be more. And this was measured empirically back in the 1700s by the French. They sent one team north to Lapland near the Arctic Circle and another team to Ecuador to make meridian arc measurements. So the guys in the north measured 1 degree to be 57,422 toises, and the guys at the equator measured 56,734 toises. And just for completeness, the actual number of miles per degree is about 68.7 at the equator and 69.4 at the poles. All right, so now hopefully everyone has a bit better understanding of 69 miles per degree, and most importantly, why it doesn't work on a flat Earth. So let's listen to a bit more derp from Whitsitt.
If you actually look into it, it's well known that like visual space is much more complex than this really rudimentary trigonometry that people try to use, assuming that there's linear visual space. And this has been tested and written about at some of the highest levels.
Cool. So most often when flirts bring up this curved visual space stuff, they're usually referring to a paper called Direct Measurements of the Curvature of Visual Space from 1999, where people such as this lovely young lady on the left here were asked to use a remote control to try to line up this arrow to this ball. So basically this is an example of what's called exocentric pointing. So imagining yourself in the position of the arrow and trying to point at the ball, as opposed to egocentric pointing, where this lovely lady just points directly at the ball, and you can't really fuck that up, right? So to be fair to Austin, he did actually refer to a different paper in the debate regarding how robots view their surroundings, but it really doesn't matter. This whole curved visual space thing is just a red herring to try and confuse everyone. If Whitsitt wants to go down this road and be taken seriously, then what he needs to do is implement it. Show us how curved visual space needs to be accounted for. So this is a video of mine from about 3 years ago, where I went and empirically measured the angle to the goalposts from varying distances. And guess what? It was all consistent with basic perspective and trigonometry. And I didn't have to fuck around with curved visual space. So like I said, massive red herring.
The refractive conditions required for, let's say, celestial navigation for CellNav, you have to use planar corrections, actual empirical measurements, then correct to even try to get the refraction. And you don't just use like Snell's law. We use planar measurements to then correct, and we can't even actually use this 1 degree per 69 miles, which is such a slam dunk for the globe. It's the complete opposite. That doesn't actually happen in reality. And then to try to make the corrections for refraction, we don't use like typical refraction. We then actually have to account for planar geometry to even do it.
Wow. All right, I did my very best to try to understand what he was trying to say here. I think he just got a bit sort of twisted up with his words, so I'll try to give him as much charity as I possibly can. So the first one, you have to use planar corrections for refraction. Yes and no, but mostly no, so I'll give you partial credit here, Whitsitt. And that's after giving you an enormous amount of charity trying to figure out what you actually meant. So there is a formula in the Nautical Almanac. The amount of refraction correction in arc minutes is equal to 0.96 divided by the tangent of the elevation angle. And the derivation for this formula does treat the atmosphere as having discrete horizontal layers. And the Almanac says explicitly that this formula is only really useful for stars that are above about 8 degrees elevation. And the reason it becomes inaccurate below 8 degrees is because of the curvature of the atmosphere. So let's say your elevation angle to a star is 45 degrees. Then the path of that light would leave Earth's atmosphere roughly 100 kilometers away from you, over the ground. And at that distance, the atmosphere has only curved about 1 degree, and that would just have a negligible effect. But if your elevation angle to the star is 5 degrees, then that light path might not leave the atmosphere for 1,000 kilometers, which means the layers of atmosphere are now at about 10 or 11 degrees off from your horizontal. So yes, the very simple formula in the Almanac does assume a flat atmosphere, but no, you don't have to use it. There are other formulas that do use a curved atmosphere, and they tend to be much more accurate at these lower elevation angles. So a good analogy here is when FLIRS bring up all these military documents that say things like planes fly over a flat, non-rotating Earth. They only make that assumption in their calculations because it makes the math easier. If they needed to be super precise, super accurate, then they would use a spherical rotating Earth and incorporate Coriolis, etc., etc. Same applies here. The simple formula is more than good enough for celestial navigation as long as you're looking at stars that aren't too close to the horizon. And Whitsitt also says this formula doesn't use Snell's law. Yes, it does. And I know that it does because I have personally derived this formula. And yes, it uses Snell's law. Now, I'm not going to go through the entire derivation in this video because that would just double the length of it and it would be boring as shit. So all I'll do is flash the slides up on the screen. And if you're a massive math nerd, feel free to pause and follow it along. Oh, Snell's law. More Snell's law. More Snell's law. All right, now we keep going until we get to the final formula, which is what I had originally. The refraction correction in arc minutes, 0.96 divided by the tangent of the elevation angle. All right, I've also thrown in the dip correction approximation and showing here with the red arrow that it also includes refraction. So that 1.20 in that formula is a radius multiplier similar to the 7/6R used in the Metabunk curve calculator. All right, second point, actual empirical measurements and you don't use Snell's law. Now, what I think he's trying to say here is that the refraction correction wasn't determined using any kind of predictive model. What he's saying here is that astronomers just noticed that the stars seemed to be out of their expected position by a certain amount based on their elevation angle, and that was just attributed to refraction. So, funnily enough, I'm going to give him another partial credit. This one's a tiny bit yes, but mostly no. So, the amount of refraction correction has been known for several hundred years. So on the left here is a table from Edmund Halley in the year 1720 or so. And he was incorporating measurements from the previous century or 2 centuries. So this has been known about for a very long time. And on the right-hand side is the lookup table in the Almanac that uses that formula that I just showed the derivation for. So if you compare a couple of the values, you'll see that they're quite close to each other. If you look at the 8 degree elevation on the left, it's 6 arc minutes of correction. And on the right, it's 6.6 arc minutes. And remember that 1 arc minute equates to 1 nautical mile. So if you took a sight to a star at 8 degrees, your position fix, might have an uncertainty of about 0.6 of a nautical mile, which in the context of celestial navigation is fuck all. If you look at 20 degrees elevation on the left, the correction is 2 minutes 26 seconds, and on the right it's 2.7 minutes or 2 minutes 42 seconds. Yeah, so now we're in the order of a few hundred meters of uncertainty. And once you start looking at stars at like 45 degrees, the discrepancy between the two tables is only 6 arc seconds. And now you're kind of getting into the realm of whether your timekeeping is accurate down to the second. So like I said, Whitsitt is mostly wrong here. We've known for centuries how much refraction affects the stars, but without knowing the actual refractive index of air, we weren't able to derive those values mathematically. And that brings us to the last quote, that 69 miles per degree doesn't happen in reality. What the actual fuck, dude? Yes, it does. And you even agreed that it does during the debate. So I don't really know how to steelman what he says here. I've been through the geometry and, shown why perspective doesn't explain it. I've showed that a globe with distant stars does explain it. I've explained why it's not perfectly 69 miles per degree because of the oblateness. I don't know. Does he disagree with refraction?
I'm claiming that you haven't even actually accounted for all the variables, and you're touting your trigonometry that literally hand waves dismiss one of the most important variables when it comes to perception, which is refraction. Refraction always happens. That's why it's important. Refraction, which we immediately and adamantly claim is always present because there's temperature fluctuation and atmospheric conditions that are consistently affecting what you perceive. Well, if you can't adequately account for refraction, you can't make a claim about the apparent location, now can you, Randy? Refraction increases proportionate to the distance, and never in your dissecting of the observations do you even account for refraction that we know for a fact to be present. And refraction, because you're increasing refractive effect proportionate to distance. So the more atmosphere you have in between you, the more refraction you have because the more atmosphere that's there. When you just throw refraction out entirely, invoking the furthest point away in the image and saying that you don't have to account for refraction and making the baseless assertion it doesn't move it because you showed us some really not very great images where they look to be generally the same is laughable, bro.
It's laughable, bro. No, we definitely do need to account for refraction. So Austin, show me where 69 miles per degree doesn't happen in reality. Anyway, you know where to find me, bro.